Hello. In this last lecture of the course variational methods in mechanics and design, we will discuss one small topic, but also an important topic of being able to formulate a differential equation that is given to you in the framework of calculus of variations. That is, given a differential equation, we want to come up with a functional which when minimized or maximized or rather extremized would lead to the differential equation that is given as an Euler-Lagrange equation. That is, we are going backwards. That is, we are given a differential equation and we want to find the functional that will lead to the differential equation when you minimize that functional by writing Euler-Lagrange equations. We will illustrate that for a system that is conservative and non-dissipative, and we will also look at a system that is dissipative and discuss how calculus of variations framework would still apply to such systems which are dissipative. Let us take a simple example and discuss these techniques. Okay. So, normally when you look at Euler-Lagrange equations, let us write that we will be, let us say, minimizing a functional j equal to integral, let us say, x1 to x2, integrand that depends on y, y prime and y double prime and so forth, and y of x is our unknown function. When you have this, we have discussed much about Euler-Lagrange equations which are necessary conditions for the minimum of such a problem. So, that we know, noting that this is an f, we will have dou f by dou y minus d by dx of dou f by dou y prime minus plus d square by dx square dou f by dou y double prime equal to 0. Now, as we have discussed in this course, this is a differential equation. This is a differential equation, and doing this way to get the differential equation, we can call a forward process of obtaining a differential equation from the minimization problem. What we will discuss now is the backward process. Can we go here? This is the reverse process, or what we can call inverse calculus of variations. Can we do that? We are given a differential equation. So, let us take a differential equation and we want to come up with extremization problem, because most of the dynamic systems which are continuous can be expressed as a differential equation, and from that we want to get an extremization problem. Extremization problem. Let us discuss this process. This actually can be done in 3 different ways. There will be one way, another way and a third way, which we will discuss with a simple example. The example we will take will be the familiar one. Let us say I take mx double dot plus kx equal to 0. It is an ordinary differential equation that describes the dynamics, or rather what we call free vibrations of a spring mass system. Free vibration because there is no external force, there is only mass and there is a spring. That is a familiar one, right. So, which functional when extremized do we get this? We already know the answer, but we will pretend that we do not know and then do it with our first method of going from differential equation to a minimization problem, that will be a calculus of variation problem. What we will do is we will multiply this with a function like this. Let us actually not put double dots there. So, we will multiply with actually another variable, just call it just y, mx double dot plus y to k x y, okay, that will still be equal to 0, that will be equal to 0 when this y is an arbitrary function that you have chosen, right. Now, what we will do is we will integrate from t1 to t2, because here when I put double dots, when I put x double dot, I actually mean it is d square x by dt square. So, t is the independent variable, okay, t is the independent variable, we have dt square, okay. So, that is why t1 to t2 m x double dot y plus k x y, and integration variable is t. So, dt equal to 0, that is obvious because we have taken differential equation multiplied with arbitrary function. So, x of t is the variable function in the differential equation, variable function in the differential equation, okay. Y of t is an arbitrary function, an arbitrary function. When you multiply that, this will be 0, that will be 0, just integrating, that is one method where we integrate. And now, we write this x double dot y term in this manner. We consider d by dt of x dot y dot, okay. When we expand this d by dt x dot y dot, we will get x double dot y, in fact this is not y dot, we will just take it as y, and then we will have another term which is x dot y dot, okay. We have x double dot y, we are writing this as d by dt of x dot y, because and minus x dot y dot, because when we expand this we will get x double dot y plus x dot y dot, which is on this side. So, we are going to replace this term with these two, okay. So, that gives us, if we do it, what we get is t1 to t2 m, okay, d by dt of x dot y minus m x dot y dot plus k x y dt equal to 0. Now, you see the first term, there is d by dt and then integration dt, that will simply be m into x dot y, and that is integrated. So, between two limits t1 to t2, and then we have minus t1 to t2 m x dot y dot dt plus t1 to t2 k x y dt 0, all right. Now, if you look at this, we would notice that we have this boundary conditions m x dot y t1 t2, normally those are the ones that will be 0 when you take away problem, and this portion we can write it together. I will just write plus t1 to t2 minus m x dot y dot plus k x y dt equal to 0. Now, let us look at this equation that we have just written and think in the reverse way, that is what calculus of variations problem will give you this type of a situation. Okay. Let us imagine that y is delta x. So, let y is delta x, because y is arbitrary, we say y is delta x. Delta x is the variation of x of t. Okay. Then this equation that we have, okay, that equation that we have will give m x dot delta x t1 to t2 plus t1 to t2 minus m x dot delta x dot instead of y dot plus k x delta x dt equal to 0. Now, this tells us from here to here, if we were to consider a functional, okay, functional j which is t1 to t2 which is half m x dot square minus half k x square dt. Okay. Let us say we are extremizing this, extremizing with respect to x of t. If we do that and write Euler-Lagrange equation, we will get that differential equation. Instead of that, let us actually say that we would like to take variation. So, let us take variation of j with respect to x, okay, that is equal to 0. Then what do we get? We get t1 t2 half m, half and x dot will go. So, it will simply become m x dot delta x dot, okay, and then we will have minus half k x delta x dt equal to 0. And when we do integration by parts, then we will get back the boundary condition which is this. Okay. What is important is that apart from this minus sign, okay, the extremization we have put, not maximization. If you look at this and this, we see that the differential equation that we started out will come when we take this functional and try to extremize. Okay. So, this is one way to get. In fact, what you see here is that there is certain symmetry in the sense that if you look at when we did, our technique is simply take arbitrary function y and then multiplied it and integrated over that differential equation we got multiplied by y, integrated from t1 to t2 and equated to 0 and replaced x double dot y with these two terms. Then what we got here under the integral sign is symmetry x dot y dot x y. Such symmetry is known as self adjointness. Okay. So, if there is differential equation or rather the differential operator is self adjoint, by that what we mean is that normally the definition we write is we have, let us say, a differential operator acting on a function v, then we have another one w that is also equal to v a w, where v and w are functions. This is like a differential operator and these ear brackets refer to inner product. Okay. Here is a differential operator, okay, and VLW are functions. These ear brackets will indicate inner product. Inner product, as we have discussed in the at the very beginning of this course, in terms of pre-Hilbert spaces and Hilbert spaces, inner product is simply for integrals. It is a function, another function multiplied, integrated over the entire domain. That is what we have here. When you look at an integral of that kind, there is x dot delta x dot x and delta x. So, there is this symmetry whichever way interchange, which is what we do over here. We are simply interchanging the role of the two functions v and w. If you get the same result, which what we will get, then this process of constructing the functionals which when extremized will give the differential equation is possible. Okay. So, many people say that self adjointness is required for doing this. That is sufficient, but not necessary, meaning that if there is a differential operator which is not self adjoint, it may still be possible to arrive at the differential arrive at the functional, which when extremized you will get the result. So, we will take a differential operator that is not self adjoint. We will take the same example. I will write m x double dot. Now, I will take b x dot also, which spoils the symmetry that we have, equal to 0. This is, as you know from mechanics, this is a dissipative term. This is the dissipative term. Dissipative terms will lead to differential operator that is not self adjoint, that is there will be lack of symmetry. So, normally we say that it is not possible, but I will show you two ways in which this also will lead to a way of constructing a problem which leads to a functional, that is when minimized will lead to the differential equation. Our usual way of doing it, as we just did, let us say again the method 1, if we repeat for this problem, you will see we want to do from T1 to T2 m x double dot y plus b x dot y plus k x y dt equal to 0. Again we will replace this mx double dot y and bx dot y with other terms. When we do that, we were able to get this x double dot y, we were able to do this, we said x dot y minus x dot y dot, which goes under the integral. This is comes out of the integral, it is actually integration by parts. So, if I were to take this and do integration by parts, so this is integration by parts leads to, so we have first okay, let us do first function for the first term. Let us take this as the first function y, integral of second function, that between the limits T1 T2 minus derivative of first function, integral of second function, right. That is exactly what we have, because when we write this term and integrate it, we will get back x dot y, right, and then this part is that comes from the integration by part second term. Now, the other one, if we do, let us say first function into integral of second function will be x T1 to T2, that is fine, that is a boundary condition, minus T1 to T2 derivative of first function into integral of second function dt, and then third one we can leave it as it is, T1 to T2 k x y dt. Now, apart from the boundary conditions, if you see, this has symmetry or self adjointness, this has symmetry or self adjoint, but this one has no symmetry. So, the first method does not work, okay. But there are two other methods that we can make it work. There is a second method, let us discuss that. What we do here is to imagine a parallel system that adds energy or generative system, because the first one is dissipative system, there will be a generative system, we will add both of them to get this. In this case, what we will do is we will define a functional j T1 to T2, the time does not change. We will have a system which is like this, m x dot y dot minus b by 2 y x dot minus x y dot, we are defining symmetrically, and then minus k x y dt. Okay, that is what we will do, right. So, this one we will say we will extremize, okay, with respect to two functions x of t, y of t. Okay. We have discussed calculus of variation with two functions where our integrand is this, that is our f. So, we will write two equations that we have. One is dou f by dou x minus d by dt of dou f by dou x dot minus d square by dt square dou f by dou x double dot plus this one double, which we do not have. So, we do not have to worry about this in this problem, that is not even there. Okay. That is equal to 0. Another one is dou f by dou y minus d by dt of dou f by dou y dot equal to 0. Let us do this. Dou f by dou x, where is x? X is there and there, that will give us minus y dot, and there is b by 2, I will put a minus sign here, that is here, and then minus ky, and then we have to do minus d by dt of dou f by dou x dot, that is over here and here. We will get m y dot and then minus b by 2 y. So, we got only y's in this equation, that gives us minus b by 2 y dot minus ky. If we do this differentiation over here, we get minus m y double dot, and then we have this is with x minus of minus. Okay, what do we get here? So, we had first y dot, it is a minus of minus, actually this is plus, we are doing x, we made a mistake. The first one dou f by dou x, x is here, that is minus of minus plus, so this is plus sign, and then here minus of minus plus again, b by 2 y equal to 0. What we got is basically m y double dot minus b y dot plus k y equal to 0. This is not what we wanted. See, our equation had plus sign here for y dot, right. So, we will find that if I do the same thing for the other equation, that is for this one, we will find that. Okay, let us do for that dou f by dou y, that will have y over here, that will give me minus b by 2 x dot, then minus ky, and then d by dt of dou f by dou y dot, that will be m x dot, then minus actually plus, because we are doing dou f by dou y dot, which is over here, minus of minus, that will be plus b by 2 x equal to 0, that gives us minus b by 2 x dot, sorry, this is not ky, because we are doing with respect to x, let us change. We are doing dou f by dou y, so y is over here, we actually get we are doing with respect to y dot, we will get actually kx. With respect to y we are doing, that will be kx over here. Okay, that is kx, and then minus mx double dot minus b by 2 x dot equal to 0. What we get now is mx double dot plus bx dot plus kx equal to 0. So, we got what we wanted. So, even dissipative system can lead to a functional, okay, which is what we have written here, which when we minimize we can get the differential equation that has dissipation. The only thing is we got two equations, we got that one and this one. This is dissipative. There is a parallel system which is generative. That is why here we have a minus sign, right, whereas here we have a plus sign. So, it can be done. So, this operator clearly not self adjoint, which we already saw over here. There was this term that was lacking that symmetry or non self adjoint, but yet we are able to get this. Not only this way, there is actually a third method that we can talk about, third method which is with an integrating factor, meaning we will extremize with respect to function. Unlike in the second method where you have to introduce another function y of t which will be generative system, here we just have this and then I put a j integral t1 to t2. So, we had half m x dot square minus half k x square dt. We know that that leads to mx double dot plus k x equal to 0, which is what we said first method, we know how to do it. Now, there will be an integrating factor e raised to b by m t. Let us see what happens. Now, our integrand is this total thing. Okay. Now, if we write the Euler-Lagrange equations, which is only one variable we have, that is variation of j with respect to x equal to 0 as dou f by dou x minus d by dt of dou f by dou x dot equal to 0. If we do this, what we get now that f is this. So, dou f by dou x will be e b m by t, x is only there, that will be minus k x, okay. And then we will have minus d by dt of dou f by dou x dot, which is only this term, okay. We already took care of that. We have now this term. So, that will give us e b by m t times m x dot equal to 0. Let us expand this. We have minus e raised to b by m t k x minus, first if you do chain rule, we will have derivative of e raised to b by m t, we will get b by m, and then we will have mx dot here, and then another term we will get this, we keep it as it is. We are basically doing product rule for these two, and then derivative of this, which is m x double dot equal to 0. Now, if you see this m and m cancel, and then there is this integrating factor that we had, it is there in all of them, that can be cancelled, everything is minus sign. What we get here is m x double dot plus b x dot plus k x equal to 0, that is what we wanted. So, even with a single function, by having a suitable integrating factor, we can obtain a functional that is extremized to get the differential equation that is has a differential operator that is not self adjoint. So, to say that self adjointness is needed to write a functional from a differential equation, it would be incorrect. It is not necessary, but sufficient. That is not incorrect, that is sufficient. If we have self adjointness, you will get it, but self adjoint is not necessary. Even when the operator is not self adjoint, we can still get these functionals, which when extremized we get the differential equation. Okay. So, that is something to note, because normally people say that if self adjoint is required, it is required. In English language it may be okay, but actually not okay. It is not necessary, but it is sufficient. That means that even if self adjoint does not exist for a differential operator, we can still get the functional, which when extremized we get the differential equation. We discussed 3 methods. One works when it is self adjoint because the symmetry is established. The second and third method, second is to have a parallel system that compensates for the dissipation in the first system, and a third method where we have identify a suitable scaling factor with which we can achieve what we want, which is to be able to write a functional which when minimized will lead to a differential equation that has dissipation and not self adjoint can still work. Thank you.